All right. Welcome back to your second lesson in the flipped classroom. Today we're going to be talking about something called the natural base E. E is a very famous number, right up there with pi and the complex number I. E is an irrational constant. Okay, so notice that I have E typed out to so many decimal places here in the notes. We refer to this as an irrational constant, and E is just one of those numbers that seems to naturally occur in mathematics. It pops up in several different places, just naturally. It's like pi we found is the ratio of the diameter of the circle to the circumference, and this just naturally pops up in the same way. E is used as the growth factor for exponential growth models in several areas of mathematics and sciences. So it is a very important number that you will run across again a lot in calculus, and perhaps if depending on what field you plan on studying in college, you'll see E pop up quite a bit. E was discovered by Jacob Bernoulli, so I'm just going to give you a little bit of history here, not too much, but it was discovered by a mathematician named Jacob Bernoulli. And it was named after Leonard Euler. So named after Leonard Euler. And you notice that Leonard Euler's last name Euler starts with an E. That's why it's called E in the first place. It's referred to as the Euler number. Okay, so in higher level mathematics, it's referred to as the Euler number. And I'm going to show you exactly how, well, not exactly how, but I'm going to show you a way that Jacob Bernoulli came across E. So essentially, Jacob Bernoulli was studying compound interest problems. Compound interest is the type of interest that you run into with savings accounts, mortgages, and things like that. And he was kind of working on some math problems, and he ran into this expression, this 1 plus 1 over x that you see here in our table. And essentially, when he ran into this expression, he kind of asked himself, what happens as x gets really, 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 really big? What happens to this expression? Okay, so we're going to set up a table here. So we have our input here in the first row, and then we're going to have our output here in the second row. So the idea is, as I put in sequentially larger numbers, as I let x get really big, what am I going to be outputting? Is f of x going to get really, really big, or what's going to happen here? And this was just this was the experiment that Jacob Bernoulli ran. So I'm going to go ahead and walk you through this, and you'll see where e comes from, and you will see where this 1 plus 1 over x raised to the x power pops up when we talk about compound interest later on in the notes. It's quite interesting. Okay, so I'm going to bring up my calculator. I'm going to show you how to fill in these tables pretty quick using some features on the calculator that are pretty cool. I'm going to save you a lot of time here, so give it a second to load up. Okay, here we go. So I'm going to go ahead and clear my screen. The way that I'm going to do this, I'm going to go to the equation editor by hitting the y equals button up in the left-hand corner. Clear out anything that you have in the equation screen here. And what you want to do is you want to go ahead and enter in that expression, that 1 plus 1 over x quantity raised to the x power. So I'm going to start off here. So 1 plus, and then in another set of parentheses, I'm going to put 1 divided by x, and then close parentheses for the overall expression, and then raise that to the x power and hit enter. Okay, so there's my expression, and what I'm going to do is I'm going to go to I'm going to hit second window, which takes me to the table set menu. You want to go up in increments of 1. Actually, it doesn't really matter. The table start and the triangle table thing there in the second line really doesn't matter. I want you to go down to this part where it says independent and make sure that the option ask is highlighted. Okay, make sure it's highlighted, and then go ahead and hit second graph, and it's going to take you to a table. Okay. And you'll notice here I've already got all my x values entered in. You'll see I have my 1. So when you enter in a 1, you're going to get out a 2. So let me minimize this. We'll start filling in our table. You guys are actually probably, since I've already done this, so you guys are actually going to have to enter in the value. So you should have a blank table, and all you have to do is hit, well, x equals 1, hit enter, and it's going to spit out a value for y1. Okay, so I'm going to come over here. When we put in a 1, you can see on the table over there on the calculator, we get a 2. So I'm going to go ahead and put in a 2. And then when I put in 10, I get 2.5, 937. And then when we put in 100, I get 2.7048. And you can kind of start to see what's happening here as I'm filling this in. As x gets really, really, really big, we're starting to come real close to this number e, 2.71828. Okay, and this is how the number was discovered. Not the most exciting thing in the world, but kind of interesting. And Bernoulli recognized it, and it turned out to be one of the most important numbers there were. Okay, so we get 2.7181 here, and then we get 2.7183, and you can see that no matter how large x gets, we're just going to get infinitely close to this e number that we're talking about. So as x goes to infinity, f of x goes to e. Okay. So keep that in mind. We're gonna pull information from that example later on in the notes. Okay, so let's go ahead and talk about compound interest, because this is where Bernoulli was experimenting and thinking about mathematics. He was looking at compound interest and asking some questions about it. So we're going to go ahead and build what's called our compound interest formula. It's an annual compound interest formula. So what we're building here is something that's going to help us analyze how much money we have in an account at a certain interest rate if we invest in a certain amount of time. Okay, so so notice here it says let ace of n be the amount in the account after n pay periods. So when they say n pay periods, it's another word for after so many compoundings, right? So n represents the number of compoundings that are going to take place. Okay. P is the principal amount. So essentially, when you go to the bank, you give them a certain amount of money to put into your bank accounts, the initial amount that you start with. So we'll say initial amount, and then we're going to let x be the interest rate, right? So just a quick note on the interest rate. A lot of times if you run into a word problem in the book, they're going to tell you the interest rate is like 8%. You need to convert that to a decimal before you use it in any of the compound interest formulas that we're going to use. Okay, so let's just start off with a concrete example here. Let's say that I have a principal of $1,000, right? So I'm going to invest $1,000, and I'm going to get an interest rate of 5%, right? So notice rather than writing 5%, I wrote 0.05 so that I don't make that mistake. And so we're going to go ahead and work with that. So let's say I'm going to compound my interest one time. So I'm going to start off here. So I have ace of 1, right? Because I'm going to compound once. So essentially I have $1,000 plus whatever I'm going to make off of the interest. So how much money do I make off the interest? Well, that's easy enough to calculate. That's just 1,000 times 0.05, right? I'm going to get 5% interest. So I'm going to take my initial 1,000 and I'm going to add to it the amount of interest that I would make. And when you run that calculation, what you get is $1,050. Okay, so let's see if I can represent that algebraically in a general sense. Let's see what happens. So we're going to say over here, ace of 1, right? I took the principal P and I added to it the principal times X, the interest rate. Okay. So on the right-hand side of this example, I'm doing a concrete example with actual numbers, and then over on the left-hand side, what I'm trying to do is represent that concrete example in a general sense with some algebraic terms. Okay, so over here on the left-hand side, I'm going to clean this up a little bit. I notice that in each of these terms here, this p and this p plus x, or this p times x, I have a p in both, right? So I can factor that p out, right? So I'm going to end up with p times 1 plus x. A little bit more compact, right? Okay, so let's compound again. Let's see what happens. So now I'm going to compound a second time. Now, we don't have $1,000 in our account anymore. We now have $1,050 in our account, right? So this is our new account balance. But before I compound again, this is my new principal, right? So I now have 1,050 as my principal, and I'm going to add to it 5% of 1,050, right? So I'm going to take 1,050 times 0.05. Okay. And when I run that calculation, what I get out is $1,102.50, right? And put my dollar bill sign on the right side this time. Okay, so let's see what happens over here in the general sense, what we get after the second compounding. So I'm taking my account balance from the previous compounding and I'm bringing it down into my new formula, right? So I'm going to have p times 1 plus x, which now represents my new principal, plus p times 1 plus x times x. Okay. And I'm going to go ahead and take a little bit of time and clean that expression up and see if I can make it look a little bit nicer. So notice what I have here, right? I have one term, I have two terms, and what each of those terms has in common is this p times 1 plus x, right? So I can factor out p times 1 plus x. So here's what I end up with when I do that, right? So I have p times 1 plus x, and when I pull a p times 1 plus x out of p times 1 plus x, I get 1, right? And then in the second term, if I pull a p times 1 plus x out of a p times 1 plus x times x, I'm left with just x. Okay. And then notice here that I have a 1 plus x times 1 plus x, so I can just rewrite that as p times 1 plus x quantity squared. Okay. All right, let's compound a third time. So I'm going to go back over to my numerical example over here, and I'm going to compound a third time. So in this case, I have $1,102.50 now, and that's going to become my new principal. There's my new principal, and I'm going to add to it 5% of that, right? So 1,000, make sure I get that right. So $1,102.50 times 0.05. Okay, and when I run that in my calculator, I get $1,157.63. Okay. So I'm going to come over here. I'm going to do that one more time. I'm going to do that one more time with my symbolic representation over here. So notice now my new principal is this, p times the quantity 1 plus x squared. So I'm going to have a3 equal to p times 1 plus x squared, right? That's my principal now, plus p times 1 plus x squared times x. So I'm trying to mimic what I'm doing over here in the numerical example and the algebraic example, just again in that general sense. So notice here in the third compounding, in the first term I have a p plus 1 plus x squared, and in the second term I also have a p plus or a p times 1 plus x squared. So I'm going to factor that particular thing out, and here is what I get. So I'm going to say, I'm just going to continue on down here. So I have a3 equals, and then I have p times 1 plus x squared times, I'm going to get a 1 plus x again, right? So if I pull a p times 1 plus x squared out of this term, I get 1. If I pull a p times 1 plus x squared out of this term, all I have left is x. Okay? And then I can clean that up just a little bit more. And since I have, I have that squared in the wrong place. Sorry about that. That squared should be on the outside. So since I have a 1 plus x quantity squared and another 1 plus x, I can rewrite that as p times 1 plus x cubed. And you'll notice that this exponent that we keep on getting outside of the 1 plus x seems to correspond to the number of compoundings that we have in our problem. Okay, so we can actually generalize this process and write a concise formula to represent our account balance. So we're going to have A equals, we'll say a sub n, right? So no matter how many compoundings we have, we can represent it with a formula p times 1 plus x raised to the n power, right? So here we go. So let's test it out. Let's see if our formula works. Now, according to our numeric example on the right-hand side, if I do 3 compoundings in this manner, I should get $1,157.63. So let's go ahead and give it a try. Our initial investment P is 1,000 times, and then I have 1 plus. Now my interest rate is 0.05, right? So I'm going to enter that in for X, and the number of compoundings is 3. Okay. So when you put that into your calculator, let's go ahead and do a quick calculation here. And let's hope our formula works. So I have 1,000 times 1 plus 0.05, close parentheses, raised to the third power. And when I hit enter, there it is. I get $1,157.63. Okay, so our formula works. Okay. So there's a demonstration of where compound interest comes from, how it was developed, and let's go ahead and take a look. I have it formally stated here. You'll see the compound interest formula. A equals P times the quantity 1 plus R over N to the NT. It's a little different than what we developed up top, and the reason being is because this is based on an annual percentage rate. Okay, so in other words, if they're telling you that you get a 5% interest rate, that's annual interest rate, so you get 5% per year. Now, if you compound 5 times per year, they're going to take that 5% and they're going to divvy it up over the 5 compoundings, because you can only get a total of 5% per year. So essentially, each compounding gets 1%. Okay. So don't get thrown off by that. So whenever we run into one of those word problems involving compound interest, we're going to be using this guy right here. A equals P times the quantity 1 plus R over N raised to the NT. Okay, so here we go. Let's do a few examples using that formula. In example number 4, they say that we have an investment of $5,000 and it's made into an account that pays 6%. So some key pieces of information that you want to pick out of these problems. Right here, this $5,000 represents your P, your initial investment, and this 6% right here that you see represents R, your interest rate, right? So they say right here, you're going to be investing this money for 10 years, right? So this is your T that they have in the problem. Okay, right. So T years, how many years are you investing? They want to find the amount in the account after if the interest is compounded in the following ways. Okay, so if we only compound 1 time per year, okay, we're going to end up with 10 compoundings, right? So let's go ahead and set up this formula. We have A, right? A is our account balance after our investment is over, so that's what we're trying to find, equals our initial investment of 5,000. And then we have 1 plus. So remember, we're taking that 6%, and that 6% is how much interest you get per year. So since we're only compounding once, we're only going to divide it up once, right? So 0.06 divided by 1. And then the exponent has to represent the total number of compoundings, right? So if we're investing for 10 years and compounding 1 time per year, oops, excuse me, get rid of that. So if we're only compounding 1 time per year for 10 years, we should get 10 compoundings, or 10 times 1, right? So n times t. All right, so let's go ahead and do that calculation real quick. should get out your calculators and plug that in, and what you should get is $8,951.24. Okay, make sure you're actually putting this stuff into your calculator. These formulas can get quite complicated, and practicing putting them into your calculators and getting the parentheses in the right spot is important. Okay, it's where a lot of mistakes are made on quizzes and tests. All right, so let's do it again. This time, instead of compounding one time per year, we're going to be compounding quarterly or 4 times per year. Okay, so we have A equals, this time we're looking at an investment of $5,000, so that's not changing. And then inside the parentheses, we have 1 plus. Now, our interest rate is still 0.06, but we're chopping that 6% up into 4 compoundings per year, right? So we're going to take that 6% and divvy it up over 4 compoundings. And since we're compounding 4 times per year, right? So n is 4, and we're investing for 10 years, we're going to have a grand total of 40 compoundings. So 4 times 10. And we're going to go ahead and calculate that, and you'll notice that we get $9,070.09. Okay, so it looks like we compounded quite a few more times here, and we ended up with a little bit more money. Not a whole lot more money, but nonetheless more money. Okay, so it's important to pay attention to how many times they compound your interest when you set up these savings accounts at the bank. Okay, let's do it one more time. This time we're going to compound 12 times per year, see how that affects our account balance. So our account balance is equal to 5,000, our initial investment, times 1 plus. I'm going to take that 6%, and I'm going to chop it up over 12 compoundings per year, right? So each compounding gets 1/12 of 6. And then since we're investing for 10 years, we're going to take 12 compoundings times 10 years. And what we get is $9,110.14. Okay. And there you have it, right? So as those compoundings go up, our account balance is going to go up. We're going to earn more money with more compoundings in our savings account. Okay, so this is kind of what Bernoulli was studying, and he asked himself, well, what happens if I compound continuously? In other words, what happens if I compound an infinite number of times? My pen going to work. There we go. Okay, so note that as n increases, so does a, but the rate of increase slows, right? So what Bernoulli was wondering is there a number that this is going to converge to if we let n get really, really big? Okay, so what happens if n goes to infinity? Well, now we can derive the continuously compounded interest formula. There's a separate formula to represent when n goes to infinity. Okay. So the way that Bernoulli did this was he did a lot of algebraic manipulation. He started with A equals, he started with our compound interest formula that we're currently using, right? So he started with A equals P times 1 plus R over N raised to the NT. Okay. And I'm gonna draw a line down the middle here because there are going to be some parts of this derivation where I need to explain a couple of things, and I'm going to do those explanations over to the right. Okay, so we're going to start here in the second line. Essentially, what he did was he said, well, let's rewrite this. Let's rewrite this as P times 1 plus, and rather than putting in 1, or rather than putting in R over N, he replaced that with 1 over N over R. Okay. Now, the reason that he did that, I mean, he didn't really change anything there. If you recall, 1 over N over R is the same thing as saying 1 divided by N over R. And if you remember how to divide fractions, that's the same thing as saying 1 times R over N, which is equal to R over N in the first place. So he's just playing around with this formula and seeing how he can change things. Okay. The next thing that he did was he messed around with the exponent of the continuously compounded interest formula, or of the compound interest formula that we were using before. Okay, so rather than just putting in an NT, what he did was he put in N over R, and then he raised this entire expression to the RT. You're probably wondering, well, why did he do that? Don't worry so much about the why. He was probably just playing around with the formula to see what he could do with it, and if he could write it in any kind of different forms. That's just what mathematicians do. Uh, but essentially, he still didn't change the formula. If we take a look at these two exponents, this n over r and this rt, it's a power raised to a power, right? So when we have a power like this, a to the x raised to the y, we know it's the same thing as a to the x times y, right? We multiply those two exponents. Well, look at what happens when we multiply n over r times rt, right? So it's rt over 1. Look at this. The n's or the r's cancel, and what we get is nt, right? Which is what we originally had before. So we really haven't changed anything. We just changed the way that it looks. Okay. Okay. So let's go ahead and take a minute here. And this is what Bernoulli asked himself. He said, well, what happens if I let n get really, really big? Okay. So he made a quick substitution. He said, let x equal n over r. Okay, and think about what happens if we do that. Okay, so he did a quick substitution, said I'm going to define a new variable, I'm calling it x, and x is going to represent n over r. Okay, so here's what we have. We have p times, I'm going to do this, 1 plus 1 over x, right? Because this n over r here becomes x. Okay, and I'm going to continue on here and close that parentheses. And then notice in the exponent here, I have another n over r. So that's going to give me an x here. And then I'm going to close off that parentheses. And now I have this rt. Okay. So why did he do this? Well, look at what happened. Okay, look at what happened. Look what we have here. 1 plus 1 over x raised to the x power, which you should recognize from the beginning of the notes. And this is kind of important because this is where e kind of comes into play, right? This is where e pops up. This is where he found it. All right, he found it in his playing around with the compound interest formula. So he asked himself, well, what happens as n gets really big? If we compound continuously, so we say as n goes to infinity, so does x, right? X will also go to infinity. Okay. So if x goes to infinity, well, we know from our previous example that that expression, 1 plus 1 over x raised to the x, is going to go to e. Okay, so what we get is p, and this entire expression that I have circled in red here simply becomes e. And that's going to be raised to the rt. Okay. And there you have it. All right, so this formula, A equals P times e to the RT, this is our continuously compounded formula. If we run into a banking problem or a savings account problem where we're compounding interest continuously, okay, we're going to use this formula. And it's referred to as the shampoo formula because it looks a lot like PERT. Okay. So how do we know when to use this formula? Whenever we see the words continuously compounded. Okay, whenever we see that in a word problem, we know that we're going to be using A equals P times e to the RT. All right, so let's take a look at a quick example. So if you recall back in example 4, we had a principal investment of $5,000 with an interest rate of 0.06, and we're investing for 10 years. And now instead we're compounding continuously, right? So there's no more n. Instead, what we know is that a is going to equal 5,000 times e raised to the 0.06 times 10, rt. Okay. So I'm going to go ahead and I'm going to put that into my calculator real quick and find out how much money I can make if I let the compoundings go to infinity. E to the 0.06 times 10, and I'm going to hit enter, and I get $9,110.59, right? And there you go. Okay, so there's an example with continuously compounded interest. All right, one last example here, and then we'll conclude these notes. Okay, so we're looking at a population of a city. Now, this exponential growth model that I gave you, this A equals P times E to the RT, can also be extended to different applications besides savings accounts. Okay, so you might recall. That P equals E to the RT. If you look at the model that they give us in this problem, this 32,000 times E raised to the 0.0367t looks a lot like PERT. And this is because PERT is not just applicable in banking, it's applicable in a lot of different situations. Anything that has any kind of exponential growth most likely uses a model similar to PERT. Okay, so the population of a city increases according to this model P of t, where t equals 0 corresponds to 1980. We want to use this model to predict the population in 2008. Okay, so if I'm looking at that model, that 32,000 times e to the 0.0367, if we assume that it's in the same format as PERT, then we know that our initial population, the initial population of this city, is equal to 32,000. Right, so we have an initial population of 32,000. And what we're trying to look for is what's the population going to be so many years later in 2008? Well, if t equals 0, right, so if t equals 0 equals 1980, then 2008 is going to be 28 years later, right? So t would have to equal 28 in this situation. Okay, so we have a growth factor of e. All right, so notice that our base here for this exponential function is e, so that's our growth factor. I'm going to go ahead and enter in this information, right? So the population, let's call it P of t, our population of this city, is going to be equal to 32,000 times e raised to the 0.0367, and instead of putting in a 0 to get my 32,000, I'm going to put in 28 years, right? So 28 now represents t. And when I do this calculation, what I get is 89,419.2 people. Okay. So here we go. Just to talk about these different parts, we have 32,000 representing initial population. We have our length of time, right? The length of time that we're letting the city grow. And E is our natural growth factor, right? So this is the growth factor of our model. Okay, so there you go. Just another quick example, just so you don't think that this stuff only relates to compound interest. I wanted you to see a different type of problem where exponential growth is taking place, and that takes place in populations of cities, populations of animals, and things like that, which scientists spend a lot of time studying. All right, well, that concludes our notes for this section. Thank you very much.